So the shear x or shear y beta x beta direction is not known yet. Until Mohr circle is constructed. If you don't construct Mohr circle, you will not know. Okay, so for now, we don't know yet. It's okay, right? So again, same procedure, protocol is the same. Okay, nothing difficult. Okay, sorry, I wouldn't say nothing difficult. Okay, just sketch it out first. Okay, it gets a bit of getting used to, right? So now we have our normal stress, and then we have our shearing stress. Okay. So we know now point X is equal to 0, right? So this is our stress X line. And the next line I'm going to draw this is our stress Y line. Right, stress Y line, right? And we know that over here, this corresponds to our point X. Over here, this corresponds to our point Y. And then from here, we can construct our Mohr circle. Okay. Likewise, we can also find the center of a circle. Right? And we know that this point is equal to P over A. And likewise, we are aware that the distance from here to here, and our distance from here to here is P over 2A. And then over here, this is our center of circle. Okay. Now this one is different because now point Y is not equal to 0 but at P over A, and then we are going to rotate this by 25 degrees. So we are aware that this angle over here is 25 degrees. So now when we rotate 25 degrees on Mohr circle, it's 2 beta is equal to 50 degrees. Okay, so now I'm going to sketch 50 degrees. Okay, so this is 50 degrees. So now you see that it's different now. Okay, so that is our Y beta. And given to us at Y beta, right, we have a normal stress of what? Of 800 times 10 to the power 3. And the shear we are given that is equal to 600. And both of these are in kilopascal, right? We are aware that both of them are in kilopascal. So we are also aware that this angle over here, right? This angle over here is our 2 beta. So this is equal to our 50 degrees. Because why is it 50 degrees? Because on element is 25, on Mohr circle is 2 beta. So from here, if we look at the shear, over the shear, the top is shear going clockwise, down here is going anti-clockwise, right? So the fact that it's going anti-clockwise, the shear stress now, the valid shear stress now look like this. Okay, so this is the valid one. Okay. These are the valid shear stress now. Okay. So from here, we we know that we have y beta, also, stress y beta. So we can calculate like what we have done before. So stress y beta, let me change. Okay. So we know that small normal stress y beta now is equal to stress average plus by tau max, right, cosine 2 beta, cos 2 beta, right? So why that's the case? So if I were to draw a line from here, right? So we know that the distance from here to here, and then we also know the distance from here to here. So we know that this is P over 2A, and this is equal to tau max, not mass, tau max cos 2 beta. Okay, so given the value to us, so before we go on, we know that stress average for this case, right, is also equal to tau max, right? And this is equal to P over 2A. Okay. So the value given to us is 800. Times 10 to the power 3 is equal to P over 2A. Now, this one is plus. The one we did before was minus. So P over 2A. Right? Then we have cos 2 multiplied by 25. So from here, we know that P is equal to 800 times 10 to the power 3 multiplied by 2. Cross-sectional area is 0.05 by 0.08. Okay, so you bring across. So this is divide. Now is 1 plus by cos 50. Okay, so this will be equal. See how much space I left. Maybe I will squeeze a bit. So this will be equal to 1 plus by cos 50. Okay, so 1.642. So 800 power 3 times by 2 times by 0.05 times by 0.08 divided by 1 cos. So it's equal to 3.896 times 10 to the power 3 Newton. Okay, so if we look at the answer, 3.896. So they have it as 3.9. Okay. Then we go back here. We look at the shear, right? So we are going to look at the shear y beta. So shear y beta is more straightforward. It's equal to tau max, right, sine 2 beta, right? Because why is it tau max sine 2 beta? Because this height over here, I'll use a different color, right? This height over here, right? Right, is equal to tau max sine 2 beta. And given to us, tau max or shear y beta given to us is 600, right? So 600 times 10 to the power 3. So this is equal to P divided by 2 and both areas 0.05 multiplied by 0.08, right? And then sine 2 beta is sine 50. So therefore, P will be equal to 600 times 10 to the power 3 multiplied by 2 multiplied by 0.05 multiplied by 0.08. And then you divide by the whole thing by sine 50. Right? So this is equal to 600 power 3 times by 2 times 0.05 times by 0.08 divided by sine 50 is equal to 6.266. Yeah, 6.266 times 10 to the power 3 Newton. So this is based on the shear, and this is based on the normal stress. So from here, you pick the smaller value, P allowable will be equal to 3.896. Okay. So this question, as I said, it can look a bit confusing initially, but it's not that bad. So now you know how to solve this. Okay. So the one before, right? The y beta is over here because at point y, the normal stress is equal to 0. Okay. Whereas for the second question, the normal stress in the y direction is not equal to 0, and all are rotated from y beta. These are some of the most confusing question in the topic on Mohr circle, either 2D or 3D. Okay, we're going to do more of it in you'll see later. We're going to do more of this sort of question in combined loading or for our normal stress and shearing stress. Okay, so that's all I want to touch on 2D and 3D Mohr circle. Okay, I've posted the homework that you can see on Avenue to Learn. And you can see two questions are very similar to what we've done today. Okay, try it. Okay, it's not that bad. Okay, right. So the next thing that we are going to deal with, okay, the next thing that we are going to deal with is we are going to look at normal stresses. Induced by centric and eccentric bending. So like the term comes, we will see we just came from buckling, right? We have centric buckling, eccentric buckling. Okay. So for bending, okay, you also have centric and eccentric bending. Okay. And I believe when you are doing 2P04, you have seen this before. Okay. So I'm going to do a very quick revision and also with an example to help you recall. Okay. But the method that I've developed is unique in the sense that you don't need to use matrices. Okay, you don't need to use a cross product and so on and so forth. Okay, you will be able to visualize. Okay, the more important is visualize when is it a tension stress, when is it compressive stress. Okay, and it's slightly different. Hopefully I find easier rather than using the matrix form that can be very confusing. Okay. Okay. Right. So in general, there are four different types. of these 4 different types of bending configuration of bending moment